you want to elaborate more on your... No? It's a yes? Okay.
Yeah. Can I, sorry, can I have the second one? This is out of my control. Okay, so let's say that actually there is a lot of things, and we will try to summarize, discuss them with you, and maybe improve or answering specific point. Let's say that this one is somehow results and perspectives. So we jumped a little bit ahead. Let's say we were so looking at the analysis of the Leendert de Boerspolder. My analysis today is, yeah, it went down. Come on. This was the day after, but let's say this is finally, eventually, it failed. But what was the true story? As we said, this was it went underwater, so we had to grasp as much information as we can from the thing. Now, sorry, obviously, well, with this slide, we don't see that much, but the failure occurred in what is called the south side, because it's a little bit southern than the north side here, and obviously everyone is looking here. Now, I will just play it for the last time, but please look here instead, in the part which didn't fail, okay? And you will see that actually the tow is going really far in spite of the fact that this didn't fail. So I don't know whether I can go back. Look at this. I mean, and this part actually, also the tow of this part somehow failed out. It disappears underwater well before, let's say, the water which is coming from the breach. Now, there was a long debate, actually internal, about, designing the failure on the 14th of October at 9:30 in the morning would have meant to know exactly everything of that dike and to ask that dike to be so kind, please. The dike was kind. We knew definitely less than everything, but the dike was rather kind. So let's say that there were various predictions, and obviously when we worked together with the TARAS in the range of these predictions, let's say I will show you our prediction because they are functional, so somehow they serve to show a few things. But this does not mean that our predictions were better. Well, obviously, on presumption, I think that they were. But anyway, let's say that in general, this doesn't mean. So we started at the end with a calculated factor of safety of 1.22. And we were, let's say, calculating, but this was, again, 2 days before, collecting all the data, a factor of safety of 0.85 in 1 minus 0.25 drawdown, and 0.79 minus 1.5. Actually, the failure occurred when the water was already here, minus 1.5. And as you saw, the entire body of the dike failed, not just this part, okay? So let's say at some time, well, okay. So the question is now, it doesn't matter, I mean, actually the dike failed in that period in which the range of prediction was. And this is, I think, a very good thing. Now, was that prediction correct? Actually, this prediction was made in a rather funny way, which is relying on soil mechanics. We used the effective strength parameters, but we didn't do a drained analysis, not at all. I mean, because in a drained analysis, the pore pressure should have been, the distribution of the pore pressure would have been something like this. We didn't use at all the distribution of that pore water pressure. Actually, we made an hypothesis on pore water pressure distribution, assuming a partially drained conditions, and the choice that we made was 1 plus 2 kPa, was made by using a reduction of the pore pressures with respect to undrained conditions of 20% based on what we had observed in the previous steps. So we said, well, more or less a reasonable consolidation somehow, because this is obviously consolidating. So obviously we didn't have a drain, we didn't use drain, we did use something like this in a simplified scheme. Now again, was the prediction correct? The predicted failure surface seems wrong. The factor of safety of 0.79 appears low with respect to the expected 0.85 or 0.9 at failure, accounting for 3D effects. But at the same time, a true undrained analysis, critical state soil mechanics with OCR based on laboratory data, seems to give a better, somehow, failure mechanism, but it gave too high factor of safety with respect to what we observed. Obviously, let's say, we are in this range. Now, one of the things that we observed just after that, and that I would suggest somehow to look into, is we have some uncertainty. Obviously, I did all deterministic analysis. Uncertainty will be on top, let's say, of this. So this is just pure average engineering. Now, let's say this is the failure surface. This is the failure surface predicted with the lowest factor of safety. But if we do an envelope, so the Bishop, let's say the safety envelope, the safety overview, if we look into all the possible failure mechanisms, this envelope is not actually circular anymore because it's the envelope of various circles. And if you look at the envelope and the area which would correspond to a factor of safety between, let's say, below 0.9, you obtain a nice indication of the type of global failure which could have occurred. And this was one of the things that in April we had understood. So instead of looking at a single one, why don't we look at all the possibilities? Because who is telling us that the mechanism is one and is circular? Now, we also compared that with the inclinometers at failure, and obviously these are displaced by meters, but you see that the maximum would be here, the maximum would be here, the maximum would be here, so that seems reasonably fine. Now, let's say, but again, when was the real factor of safety and when was failure triggered with reference to this value? Well, instead of looking just at the mechanism that we could roughly see with the inclinometers, we went and looked into what the displacement rates and what the pore pressure rates were in time. So how, let's say, it accelerated, but just by looking at 1 or 2, 3 things on a screen as we had in the night of the failure when we saw the things accelerating, but just looking at how much and where and which time. Now, let's look, for example, at this point. Peat, let's say we call it peat 2, because actually this peat is made of 2 different peats. Not that different from each other, but in any case it's just 2, maybe more than 2, but let's say a moss peat on top and a sedge peat on the bottom. Now, let's look at this. You see that here at exactly 5:49, Stefano asked me to be precise. He's very precise. In spite of being Italian, he's called a German. So 5:49, not around 5:50. That would be the Italian approximation. 5:49, you see that, let's say, the relative displacement between these 2 points, these are distant 50 centimeters, so we don't know what moved there, because we just have 2 points. It could have been like this, it could have been 20 centimeters, can be the entire 50 centimeters. So with a rate that ranges by, can ranges by 5, but it was clear that it started. And the same, well, you see that some disturbance also in the pore water pressure here. Then I go on, and exactly at 5:49, you also see the same thing here. Well, here something had happened probably before in the organic clay, but in any case, again, it raises the velocity. Again, the pore pressure goes down. And if we look at these 2 points, it happened the same. So, let's say, 5:49 was, let's say, in our opinion, at the end, the onset of the failure mechanism. It took, let's say, the final failure mechanism. So when all the points in all the entire line started giving, accelerating for some reason, and with the pore water pressure going down at the toe, which meant that it was a sort of at least partially undrained failure at the toe. Now, 549 was during the third dewatering, was not at the end. So it was already during the third dewatering, which means that the water level there was in between 1 and 1.5. Now, this factor of safety starts becoming probably more realistic if the failure was triggered there. Let's say that the failure mechanism was triggered during the third pumping stage. Then it accelerated and went on, but that is a story. Can we better identify the shape of the mechanism? Let's go one step back. So we are not happy with 549, and let's say it's a rather tricky thing, but let's say what we looked into was the change in the type of deformation, which means that through the extensometer and the inclinometers, we could have an idea on what was the ratio between the vertical strain, the vertical deformation, and the lateral deformation. And this was going nicely, for example, at the toe of the pole, it was going nicely on in some sort with the same type of deformation. At some stage, it changed, and you see here that, well, irrespective of the values, but now the horizontal strains, the horizontal displacement, accelerates more than the vertical one. So the type of deformation changes. And the same happens with the pore water pressure. So as soon as this starts going faster in the horizontal way, then also the pore water pressure, as it is dilated, go down. The German went through all this data very precisely, and he was able to give us some sort of, let's say, time of displacement. This happened at 5:13 a.m. At 5:29 a.m. also the upper part, well, with all this part which is dilated due to the previous reason. And then at 5:30, so something like 2-3 minutes later, but sometime later than this, these two moved, both. So here, if we look at the inclinometer in the middle, we have two distinct localized somehow failure. A little bit later. And then a little bit later, 5 minutes later, also the one in the pit started changing its mode of deformation. And then we arrived to 5:49 a.m. in which these started. So actually, in the end, what happened is that this is a sort of, let's say, it's not a circular mechanism which came down like this, but it's a sort of mechanism in which this part moved first, and then this went down, and then this one, and then this one. I mean, I cannot say that it was a retrogressive failure, because when we look into this, the displacements are still, let's say, very small. We are in the order of the centimeters, while only when everything was activated, slowly it went towards failure. But while at 5:49 everything is moving, let's say the first signals were here. Now, this is a preview. I'm not tricking again. I was surprised when I saw it. If we do a plexus analysis with the right parameters, and let's say if the mesh is very, very somehow refined in the area in such a way that we can really catch nice things. Actually, also the plexus analysis shows systematically two potential shear failure. Now, if we look at this, and if we think that this mechanism could have been activated, then this one resembles definitely more this one. So the reason why we couldn't understand, in my opinion, why the Bishop failure, the Bishop overview was able to catch the better somehow the shape of what the final failure was, is the fact that actually the Bishop overview is the shear envelope of all these possible shear failure which are there and will happen anywhere because of, let's say, the weakest link or any reason. So let's say that even the praxis analysis showed that at various stages you could have more than one slip failure going. So going even back to the origin, the pre-failure deformation mechanism, well, I go rather fast because I have other results, but the pre-failure deformation mechanism is that actually until some stage, in our opinion, let's say that this was somehow, I cannot use squeezing, but it was just bulging out. So obviously the mechanism started with a peat which was bulging out. And the nice thing is that if you look at, well, this is not that much a case, but it's so nice that, again, it's surprising. If you look at the water content distribution, somehow this reproduces, and it's logical because the compressibility of the material, the single materials, are dependent on, are somehow proportional to the water content. So obviously, at the very beginning, before failure, this is somehow just a lateral deformation of the entire system. But then at some stage, you see that the failure starts, not the failure starts, or even during the second pumping, at some stage, slightly, but also the, let's say, this, let's say, interface moved or started accelerating a little bit. Then the pumping was stopped, it was refilled again, and so everything stopped there. But there were somehow the signals or the marks of what would have been the failure even the week before. And looking into the response of the pore water pressure the week before, we could get a reasonable prediction of what it would have been. Now I go fast. So what was the deformation mechanism? To answer you whether it was a slip circle or not. Actually, it was an horizontal bulging of the peat layer. This is our interpretation, then obviously we can have. Then the interface peat clay layer was sheared until localized failure occurred somewhere, localized in something like this. We don't know where, but because we have only 2 points there. And then partially developed, we don't know, because it was underwater. We didn't see floating peat everywhere. But in any case, it was underwater, and I cannot say that it didn't move really at the toe more. Shear mode at the toe allowed deformation of the dike body, which eventually collapsed the dike. The estimated factor of safety seems to be a more realistic value with respect to the 79, which was associated to the failure. And actually, it was somehow anticipated during the second pumping. So that's why we eventually were able to get there. And now this is a plot of looking just at the last point on top, looking from top, and you see that actually the type of deformation during the second pumping, blue lines, are exactly identical to the one which actually then characterized the failure. So we had some marks that we could use for the second one. This is not a trick. We started doing a 3D analysis. This is really preliminary, really preliminary. You have not paid for that, so you're kindly invited, not maybe 5 million euros, but let's say something a little bit less. We started doing let's say a 3D analysis, thanks to a guy who started an internship at Plaxis and worked with us at TU Delft. It was a cooperation with Ronald. Very simple analysis, elastic, linear, more Coulomb, really very simple. But the nice thing is that what the guy did was a sort of check, more or less, of the ratio between the factor of safety in similar situations, obviously with a similar type of elements and with the same type of nodes, because otherwise we can get whatever we want. From a plane strain analysis, an extruded plane strain analysis, which means that in praxis the tetrahedra will not allow a complete plane failure, and a 3D. I was, again, puzzled and surprised yesterday, so my presumptuousness is going up and up and up. about the fact that for the excavation, the ratio between this one and this one is actually 0.85. There is also a numerical issue in between, so it must not be necessarily 0.85. And for what concerns the following pumping, it was 0.88. So we are actually in that range, 0.85, 0.90, let's say 10, 15%, probably prudentially 10%, not more than that. This is partially due to the 3D, and this is also including the geometry of the real geometry of the dike. So that's nice. The analysis, well, this is not perfect. This was done yesterday, but let's say the analysis is not perfect because actually the dike in Plaxis failed on the other side. But anyway, we can be happy for our first analysis. So this is going down, actually, not this part. But let's go on. I don't know. Maybe rapidly 5 minutes, and then with some going back to a limit analysis method. We did a number of things, and I just picked up the things which in my opinion are more important. These were the parameters. Let's say Bishop or Spencer. Well, actually in this case, especially if you used somehow Bishop, the Bishop envelope, but also the Bishop envelope was not that far from a sort of circle in the end. So Bishop of Spencer, they gave more or less the same factor of safety. They gave more or less the same shape. One thing is that, in my opinion, as a, let's say, somehow indication, I would say one Bishop circle is not enough. Spencer is rather difficult to tune, because if you put, well, actually you can obtain what you want by just constraining the surface. So what I would suggest is to go from one circle to this one, and then giving sufficient room for Spencer to find the right one. And with a sufficient number of points, because if you use two less, then you have a sort of thing which has to move like this, but with too many points, then you will get a sort of wavy surface. So you have to balance a little bit and work a little bit more on that. Now, impressive, the role in this case, but that was obvious, of the pore water pressure at the toe. But this is obvious because most of the resistance in the end is here. So this is very light. It's 5 kPa, well, to be 5 kPa as a whole, which means that 1 or 2, 3 kPa change in pore water, in the assumption of pore water pressure, will change a factor of safety a lot. So we did different assumption about afterwards, about possible. We were not. It was not clear for us whether here we had the. It was indicated that there should have been a pipe, but we didn't know whether it was working or not. There seems to be some sort of gradient there, but, well, was it working? Was it not? Probably not, obviously, in that moment. So we did various assumptions, just very, if you see, with respect to the entire body of the dike, it's just assuming that it's a little bit more wet, less wet, and this is the results that we obtained. So with just those different assumptions, they're not changing really that much, but we started from, let's say, 1.2 or 1.1, but then with a complete, let's say, undrained dike, full pore pressures corresponding to a perfectly undrained conditions, we would have obtained this, which obviously doesn't make sense. The more reasonable thing gives us these two. And in the reasonable one, let's say again, Spencer and Bishop. In this case, because of the way in which it failed, it doesn't change. I think that this is an interesting thing. I'm not pointing against any of these regional data, but we use the, let's say, the regional data. These are obviously characteristic value. In order to design the test, we used the average peak values because we needed to win all the resistance. So obviously this is a little bit unfair, let's say, an unfair comparison. But let's say, in my opinion, if the real, let's say, if in the original conditions using the parameters which were used afterwards and which predicted rather well the failure, we had something like 2.19. Doing the same thing with using the regional parameters is 1.28. And in my opinion, well, this is characteristic value. I'm not an expert of characteristic values, but I would say that the decrease of this type is really big. And why is it big? Well, actually, because if you look at the friction angle, well, if we go back, we don't, but the critical state friction angle of the peat, of this peat, is 43 degrees. And this value, which is here, is 13 degrees. So we have something, let's say, which has an envelope which is cohesion, let's say 3 kPa, and slope, which is 29 degrees. Critical state friction angle, 43 degrees. Reasonable, I mean, all the data. And we're using 13. Now, is it relevant? We tried to check whether this was relevant. So we compared in one of these, for example, this one or this one, in the third excavation and pumping, the contribution of the dike material, which is this brown, and of the peat, which is this green, in terms of the entire resistance along the failure surface. So unfortunately, we got 50-50 at the beginning. So we couldn't say, we concentrate on this because this is relevant, this is not. The other thing is that we said, okay, well, with the parameters that we're using, is cohesion or friction making the, let's say, doing the dirty job? 50-50. Okay. Then, which means that we really need, we cannot disregard any of this. But if we go on, obviously, the pore water pressure are going down at the toe of the peat. So the peat is increasing its contribution in strength because in the dike is not changing that much. I mean, the effective stress is not changing that much, while in the peat is changing a lot because of the pore water pressure which are going down. Obviously, the contribution of cohesion, which does not depend on the pore pressure in our in our simple model, is not changing. But if you look at the end, well, sorry, at the very end, now you see that the contribution to the total strength along the failure surface of the peat is 75%. Well, at least in this analysis, but just to show that this is increasing. And friction angle weights more or less 50% of the strength of the entire system. That's why bringing down the friction angle from 43 degrees or whatever, 30 to 12 or 13, obviously makes a lot of difference. My question is it necessary? Can we maybe look into, well, collect more data, try to do better collection or statistics or checking a priori the data in order to have not so large statistics that will hinder, well, will bring down a lot the thing. Now a few finite element analysis, well, maybe this is not that relevant, but again for the, let's say the finite element analysis, Plaxis analysis, so we were working with standard tools. Actually, again, there is a lot of influence on the factor of safety on the pore water pressure distribution at the toe. But in the Plaxis analysis, they depend on consolidation. So they depend on the permeability that we give to the analysis. Which means that by changing just the permeability of the peat by an order of magnitude of, sorry, by 2, so just by doubling it, which is in a range, in a small range of the possibilities, we get factor of safety which goes from 0.6 to 0.7 and so on. So really, let's say few conclusions. Again, I was surprised when I saw this combination between some, well, obviously I chose the best one. In this case, I tricked. I chose the best one of our 100,000 attempts. But let's say, this light blue is the measurement until the second, so this was the first excavation, sorry, the second excavation. And let's say, we got pretty good, obviously with, well, differences that probably we can discuss later on. Now, 3D versus 3D, competitive in back analysis of a failure, obviously, because we have 3D effects there that we cannot, we will never be able to catch with a 2D analysis, but it's not competitive in assessment. The failure altogether took 6.30 minutes, so 6 hours and 30 minutes. The calculations of the failure took 2 days. Okay, so obviously it's not that competitive in terms of a normal tool, but I would say that in analyzing the result of such a test, it is somehow competitive because otherwise we could try. Extremely sensitive to hydraulic conductivities in this case because we forced it with change in pore water pressure at the boundary. That was the only way. But in any case, let's say this might not be a big issue in assessment because we're not referring in general to time dependent, but might become very relevant in the reinforcement design because we have to choose timing. So how long should we wait? What should we measure? I mean, how can we go rather fast but without going too much near to failure? And let's say for what concerns, again, a simple effect, let's say that the sensitivity analysis, for what, I mean, remaining in a sort of, let's say, deterministic framework, there was some idea of factorizing other parameters which are not, let's say, the shear strength, so the stiffness or the permeabilities and so on. It's too difficult, well, apart from the fact that, well, it might make sense, but it's too difficult to get a priori what the characteristic condition would be. The lowest stiffness, the highest stiffness, the lower permeability, the highest permeability in which layer and what. So, well, actually even around the idea is no factorization. As the worst combination is difficult to find, do some sensitivity analysis on the parameters that you consider important. Let's say, Tom, should I skip the heterogeneity? Anyway, you see here, well, in this table that Tom prepared for you and that I will not show to you, well, there is an order of magnitude in the coefficient of variation between the dike and the rest. Now, we can go fast because just the last thing, and then we don't have time, so okay. But it was, all the country was enthusiastic. Obviously, we were enthusiastic. We were flying, let's say, over the country. And we were looking at all the sites in which the news was reported, while you were getting a prize for the test. And that day, I was particularly puzzled by this one. Let's say there were many girls on site, and really many doing a lot of work, a lot of true work. And well, I picked up a student because I didn't want to pick up either Tom or any other, let's say, grown-up boy, but this boy, the only thing he's doing is looking at these people working. Are we sure?
Yeah, I can tell you that when I started my study here, we were with 300 students. 3 girls, only 3 girls, so that's 1%, and I think that's improved in time. I think, and when I was here, I never had a female professor, and now we have. So there is some improvement, I think. Yeah, that's strange. Italian. Yeah, that's that's the most difficult point. For a Dutchman. Okay. Vragen.
Thank you. My name is Marieke de Visser. I work for Rijkswaterstaat. In your stability analysis, I was wondering, what kind of soil parameters did you use? Did you, you said it was a deterministic evaluation, but did you use average values or characteristics or design values? Because that also could, well, have an influence on the results and the shape of the circle.
Definitely, because obviously this is, let's say, a system made of various things, as well as the ratio between the stiffness also plays a little bit because it moves a little part or another. Let's say that I'm trying to keep far from all these characteristic values, in the sense that what I would like to do, I mean, in terms of my contribution, well, we are somehow still working on the characteristic values somehow of the area, of the boulder. So the idea is, let's say, the characteristic value of regional are there, and the difference is somehow dramatic. Now we have enough data to get characteristic value statistically significant of the boulder, and on another area, which is something like 80 meters apart. I can't remember by heart, but 80 meters apart, and applying that model. Somehow, all the aspects related to even a better reliability analysis in terms of the information that we have is going on now with the STW project, which is will be presented by Michael Hicks this afternoon. So I completely agree with you, but the main point is our characteristic values, are they, can we do better, or do we have to go on using, let's say in a big area, characteristic value which are really very low with respect to the, we use the most likely value, obviously. And this is what you have to do when you have to compare your analysis with the result with monitoring. Otherwise, obviously, you do not get anything. So we use the most likely. Definitely. The dike could give you whatever. Actually, what we did, in the sense that considering that it's completely different material, you can get completely different values in general if you put the things together. Obviously tested on those samples of soils that you can test, because if you find cast iron, you cannot test it. Neither really something like this of muscle skeletons. I'm not joking. Let's say on average, you have the typical value for a silty sand, dilatant silty sand. Then we can start discussing what if we should we work on the parameters? Should we work with what was our job in trying to understand what happened, instead of doing some sort of, was to try to get to choose, not to choose, but to eliminate those data which were just outliers in a picture which was geotechnically consistent. I understand that this is not a procedure that you can use daily. It took us months of work. So, I mean, it obviously was just to try to understand the best we could this area and use this understanding for future development, but not just doing standard calculations. Although we performed some, obviously, in order to, and we can perform more. I mean, a limit analysis is very quick, so we can discuss that further, for sure.
Wie anders? Who else, I said.
Henk van Hemert, and I make this remark on behalf of STOWA, which I wish to express. No, it's, I do it in English for you, Professor Jommi, in order to understand, but I think I'm targeting the audience, because I would like to put one of your remarks in a little bit different perspective, if you allow me. It's a remark on the planning, on doing 16 months of poldering and 1 month of measurements, and I feel obligated to reflect on that, because as far as I remember, as soon as the opportunity of the Leendert de Boerspolder came in the right group, the geotechnical expert group of STOWA, I think the decision to do the test, including finding the budget, was made within 1 month. And then indeed afterwards, doing all the different stages of the site investigation and discussing on why and all the administrative constraints, that took a lot of time. But the real decision to do the test was made within 1 month, and I'm less accurate than a German, but I think it was more or less 1 month. And I think it's important to mention, because I used Leendert de Boerspolder sometimes as an example, that if any research proposal is good, the decision is taken fast. So sometimes the speed of the decision-making process I use as okay.
Consequences that you were very good. We all were very good, and I almost agree. What I mean is that it took 16 months. So I also say that during this period, in any case, let's say the investigation started. We had the first stage of the investigation, then the second started. We had a lot of time to do laboratory tests at TU. We do not have a lot of equipment, so we're a little bit slow, but we did a lot of things. And this gave also these guys and another 2 people the opportunity to have a lot of information which is not usually visible. So obviously, well, I have to go on. That was the last slide, but I was obviously, all these people really contributed. And yeah, the decision was taken. I do agree. Sometimes I felt myself, but that is also understandable, that the thing were slowed a little bit down, because I think that we made, together with the other people, good choices with a reasonable budget, but it was a little bit, let's say, hard to go on with a research plan which had a clear target. And by the way, the 2 guys, thanks to you, thanks to STOWA, and thanks to all the other people, got their final salary in December 2014. So, you know, it was a little bit stressing, because it was a little bit jump, but we were good. Starting from this one, that are not that big for by chance. They're big because they played the role. Obviously, this is a STOWA day, so.
Thank you. That's too much honor. It's good, Cristina. Thank you for your presentation, but especially to show you this slide, because we doesn't often work in collaboration with 7 water boards, 3 provinces, Deltares, and the TU Delft. So this was really a unique project, I think, and I don't have to mention the guys who were the guys and girls who were the strength and the power behind this project. Thank you very much.